One of the main uses of valence bond theory is in describing the structure of bonds. It'll tell us what the electron clouds around bonds look like, and this is very important for you in organic chemistry when you're trying to understand how a reaction works and how you can predict the products of their reaction. So you will see this again in more advanced courses. Let's take a look at a simple single bond, double bond, and triple bond system and see how we describe those in the valence bond theory. So we've seen that if you have H2, the bond between them looks like a simple overlap between the 1s orbitals. Let's do one a little bit more complicated. Let's do F2. Okay, we want to do the Lewis structure first. There's the skeleton. It's got 7 electrons for each fluorine, so there's 14 altogether. I put down 2 to connect the structure, and I have 12 left. I satisfy the octets on the outside atoms. So the Lewis theory tells me I'm going to have a single bond between the 2 fluorines in F2. Let's see what the valence bond theory is going to tell me. What kind of electronic geometry do I have around each of these fluorines? I've got 4 clouds. So I'm going to have a tetrahedral electronic geometry. And then the shape that I'm going to have is an sp3 shape. So I can draw this shape over each of the fluorines. So every time you have a tetrahedral electronic geometry, you can stamp down a shape that looks like this. So let's draw one. There'll be one that comes in and one that goes out. So this is the tetrahedron. I've drawn it tipped over on its side, and this is where this fluorine is. One of the lone pairs is here, one of the lone pairs is here, one of the lone pairs is here, and this is the bonding orbital. The other fluorine is going to also have an sp3 hybridization. So it's going to look like this. I just draw a little tetrahedron with lobes that point to the points of the tetrahedron. And this thing here is the overlap. That's the valence bond in there. That's where those 2 sp3 orbitals overlap. Now, that kind of bond, when you have sort of head-to-tail overlap, is called a sigma bond. The overlap is on an imaginary line between the 2 nuclei. So you can say this is a sigma bond. You can write the Greek letter sigma, or you can say a sigma bond is a valence bond that touches the bond axis, let's call it. What do I mean by bond axis? I mean, that's the imaginary line between the 2 nuclei. That's the line that I drew there in the Lewis theory. The bond axis would be a straight line between those 2. And if the overlap is touching that, we're going to call this a sigma bond. All single bonds are sigma bonds. Now, there's some weird exceptions to that, but you wouldn't see those unless you were in a much more advanced course than this. So essentially, for any common molecule that you're going to see, and you see a single bond, that's a sigma bond. So if someone says, here's the Lewis structure for this molecule. and they ask you, how many sigma bonds are in this whole molecule? You'll say, well, there's 4 single bonds. So 4 single bonds is going to be 4 sigma bonds. There's one there, there's one there, there's one there, and there's one there. Okay? So you can count sigma bonds now in things with single bonds. What about a double bond? Let's look at O2. That should have a double bond. Here's the Lewis structure for O2. 6 and 6 is 12, right? And then I'm going to connect the structure. That took away 2. I have 10 left. 1, 2, 3, 4, 5, 6 satisfies this one. 7, 8, 9, 10. Okay? Now this one's not satisfied. It doesn't have an octet. So, but what I can do is share a lone pair with the neighbor. So I can take this lone pair here and move it down as a bond. So if I do that, I'm going to get a double bond. And that's what the Lewis theory predicts for this. We should have a double bond. Now in a double bond, we're going to see that the first bond is a sigma bond, but the next one is something new. Now, what do you think the hybridization on these atoms is going to be? Ask yourself, what electronic geometry do I have around each of these oxygens? I have a lone pair, another lone pair, and a bond. Remember, that counts as one cloud. So that's 3 things. So if I have 3 electron clouds around the central atom, I have a trigonal planar electronic geometry. And then the hybridization is going to be sp3. So what I'm going to do is draw an sp3 shape. On each of those oxygens. Now keep in mind that these are all 3 different orbitals. I'm going to color them different just to remind you of that. Those are 3 sp3 orbitals. Now what about the other oxygen? It's going to have that kind of shape too, an sp3 shape. Okay, and there's the overlap, and that's a sigma overlap. So I see a sigma bond in there, and that's the first of these double bonds. But what about the second bond? Where does that come in? There must be another overlap. Now, what I have on an sp2 shape is an unhybridized p orbital. And that's going to go at right angles to the trigonal planar orbitals here. It's going to go up and down. I'm going to exaggerate how long it is, just so that my drawing is a little bit easier to look at. But this thing is an unhybridized p orbital, and there's one of them on each one. Now what I can do is side-by-side overlap those p's. So imagine that these are not as skinny as I've drawn them, but they're actually fat enough that they overlap like this. Now the overlap is going to go in 2 places. That's one overlap, but it has 2 parts, and neither of them touch the bond axis. This is a special kind of valence bond called a pi bond. A pi bond is a valence bond that doesn't touch the bond axis. Now it's important to know with a pi bond that this is all one pi bond. It has 2 halves here. These aren't 2 pi bonds. That's just one pi bond because there's one pair of orbitals. So it's like I have 2 hands here and I overlap them like that. This would be like what a pi bond would be like. A sigma bond would be more like that. Okay? So now, whenever you see a double bond, what you can think is the first bond is a sigma bond like that, and then the second bond is a pi bond. So you can count sigma and pi bonds when you've got a double bond present. So suppose I have this molecule, which we looked at in the last video. And I see that on a test and they ask me, how many sigma and pi bonds do you have? You're going to say there's a sigma, there's a sigma. The first one of these is a sigma, so there are 3 sigma bonds. And the second bond is a pi bond, so there's 1 pi bond. 3 sigma bonds and 1 pi bond in that molecule. Okay, finally, let's do one with a triple bond and see what that looks like when we draw a balloon animal structure for it. Here is the Lewis structure. I'm just going to do it really quick. It's got a triple bond in there. Now, what kind of electronic geometry do you expect around the nitrogen? You should say linear because there's a lone pair here and there's a bond there. The triple bond will count as 1 electron cloud. So you have 2 things there. 2 electron clouds. So you'll have a linear electronic geometry. And you'll have an sp hybrid going this way and an sp hybrid going that way. So I'm going to draw this shape on top of each nitrogen atom. So here's one of the nitrogen atoms. It's got an sp going this way and another sp going that way. This one is going to hold the lone pair, and this one is going to form a bond with the other nitrogen. Now here's the other nitrogen's sps. So this, it has 1 sp going this way and 1 sp going that way, and I can see in here that there's an overlap, and that's a sigma bond. That's the first of these 3 bonds, is that sigma bond, that overlap. Now, what about the other 2 bonds? Both of them are pi bonds, and they're formed by side-to-side overlap of the p orbitals. So now there's a p orbital that goes out this way, and that one can overlap like this. There's a pi bond there. That's 1 pi bond. Both of those. And then there's another unhybridized p orbital that goes up and down. So what you've got there is an overlap this way and this way. That's the second pi bond. So there are, first bond is a sigma bond and a multiple bond, and all the rest are pi bonds. There are 2 pi bonds and 1 sigma bond here. So let's do another example. Suppose I've got this molecule, and I ask you, how many sigma bonds and how many pi bonds do you have? You'll say, well, single bond is a sigma bond, so there are 2 sigma bonds like that. And now, if it's a triple bond, the first bond is a sigma bond, and then the next 2 are pi bonds. So in this molecule, there are 3 sigma bonds and 2 pi bonds. This is most of your worksheet for today. They're asking you to count sigma bonds and pi bonds. So what do? You have to write down the Lewis structure first of all. And then second of all, you look and see whether you've got single bonds, double bonds, or triple bonds. Single bonds are sigma. Multiple bonds have the first bond being a sigma and the rest being pi. And you should be able to finish the worksheet with just that.